it's not like that.
All I do is homework. I go home and read the textbook.
When you have kids, it's a little bit different because I get to retake, the 2nd grade and 6th grade right now. I can re-experience 6th grade and re-experience the 2nd grade. Yeah.
I don't think I want to.
No, I don't think I want to experience 6th grade again.
All right. So we were just about to talk about the binary search algorithm last time, and that's where we'll continue to talk about today. Just to make sure that it's recording. It is. All right. So binary search is really cool because the number of comparisons only has to increase by 1 when you double the size of an array. And last time I think I also showed you the big O notation. Okay, remember the big O notation, which is kind of like an estimate of how long an algorithm needs to finish a task as a function, or how it relates to the size of the problem itself. That's the big O notation, or the purpose of the big O notation. It does not take into account that some computers are faster than other computers, because that is not important. Now, how can that not be important? Well, remember last time I said that I would give you an example. A software company is downsizing, and it's down to me and another developer, and my boss has to decide who gets to stay with the company, and decided to make that decision based on a competition. Okay, see who can write the fastest program. Okay, quote in quotes. Okay, so this is the scenario, and I will just use a spreadsheet to write it down, because there will be some computation that will be very handy to use a spreadsheet for. So I'll just start at both ends using a spreadsheet. All right, so in this spreadsheet, the first thing we'll do is to talk about the speed of the computer, or what type of computer we're using. So tax computer. Now, because I joined the company back in 1995 or so I have a computer that has not been upgraded ever since. Okay.
So you got a 486 DX with the.
Let's say I have a 486.
Wow.
Okay, so the tax computer is a 486
Do you have
DX, which is already
processor? Mathco processor?
Mathco processor. It doesn't matter in this case because for sorting it's not useful. So let's say mine is running at 66 megahertz. Okay, which is a really fast computer.
For 486.
You can run Quick 1 on that. You can run Quick 1 on that.
I can probably emulate a computer faster than that, using a $300 computer today.
Yeah.
Okay, so how should I call my colleague? Let's call my colleague Pat. Okay, so Pat's computer is a modern i7 computer, quad core, running at
hex core.
Hex core, the top of the line. Okay, hex core. What is the speed of the processor these days?
3 gigahertz.
2.5. Okay. They really can't push the clock speed any further because of they're running up against physical limitations now, so they can't really push that anymore. They're now pushing for more cores on the chip, to increase the overall speed of the processor. Okay. All right. So in terms of the speed ratio, what would be the ratio? What would be a good ratio here?
1,000,000.
Well, I would probably not call that 1,000,000. Okay, the 486DX came out in what year? Okay, let me just search for that. Okay, 486DX and Wikipedia. Introduced in 1989. So I think I might have I might be off a little bit here.
That's pretty cool.
Okay.
Pentium 1.
Okay, so let's just say it is from 1989.
More than 200.
Now I don't really have to do anything to. Why is it? Okay, there we go. Okay, I don't really have to do anything to do the speed estimation because I understand Moore's law. Has anyone heard of Moore's law?
It doubles every 18 months.
It doubles every 18 months. Very good. So now we have 1989 up to 2012. So how many 18 months, approximately how many 18 months have passed in between? So 12 years plus 11 is 33. Okay, there are 33 years in between. No? No, I got it right. I'm not that old. Hold on a second. Okay, 12 plus 11 is 23. Okay, so
I was
23
gonna say,
years.
I'm in the wrong math class.
Yeah. Okay, 23 years. Let's call it 24 years because in 24 years, the number of 18 months is even. Okay, so in 24 years, how many 18 months do we have? We have 18, 16, 18 months. Okay, so we have 16, 18 months, and we remember we say that for every. Okay, I'll just rewrite it as 16, 18 months. So that means the speed of a computer of the same price would have increased or would have doubled 16 times. So that means the factor is 2 to the power of 16, which is 65,536. Okay, not quite a million times as somebody said a little bit earlier, but it is still a lot. Okay. So that means the factor I have to think about here is if it takes me, if it takes the other computer 1 second to do something, it will take me approximately we'll just round it down to 60,000 seconds. Okay, it's still a pretty significant number here. Okay, even though it's not quite a million, it is still significant. Okay, so right off the bat, I'm at a slight disadvantage because my boss doesn't really care, what computer we are using. The boss is just going to use a stopwatch. Okay, start processing, it's done. Stop the stopwatch, and then whoever takes the least amount of time will win the competition. Okay, whoever loses gets to pack up and leave the company. All right. So is that okay so far? Does everybody understand what I'm showing here, the numbers? Okay. So and because of this, the boss says, okay, let's try to write search algorithms. Okay, search algorithms, which is our current topic here, and we'll switch back to Wikipedia, and we'll look at linear search. Multiple issues. Maybe I should go in and fix it. Okay, this is the pseudocode of linear search in a particular way of in using pseudocode. It doesn't look too hard. Let's go ahead and take a look at binary search. Binary search. And in binary search, we go to the pseudocode because that's what most people would look at first is the binary search. So we'll take a look at where's the pseudocode?
Scroll through real quick, it might be faster.
Okay, right there. Okay, that's good enough. This is a little bit more complex than the other one. Okay, it involves more code, more conditional statements and stuff like that. So Pat decided, my competitor, my colleague, but now turned into competitor, decided that he will just use, or he or she, that's why I used the name Pat, gender neutral. So Pat decides that he or she would want to use the simplest algorithm, thinking that because the computer is more than 60,000 times faster than mine, there's no way that that he or she could lose the race, right? So he would just pick the easiest algorithm and be done with it. And I would just I use binary search because I think binary search is a very efficient algorithm. So I pick binary search. And the boss says, okay, let's start a competition. Let's start with an array of 1 item. Okay, fine. Okay, so here we have problem size. Now the problem size in this case is really the size of the array. The bar A bar, the size of the array is the problem size. And here we'll break into my section and also Pat's section here. In my case, I have to record the number of comparisons that I have to perform, and in the other case, we will also do the number of comparisons. Maybe rule. Okay, and this here we'll talk about the duration. How long does it take for the algorithm to finish? Okay, so we'll go change the sizes of the column a little bit here. All right. When the size of the array is exactly 1, how many comparisons do I need using binary search? 1. I mean, I need 1 to confirm either that is or is not the value that I'm looking for. And the duration is going to be, this is all just scaled. So all I have to do is to say, let's see, what would be good. I'm trying to determine the unit of measurement here, whether I use seconds, milliseconds, or so on and so forth. I'll just call it 1 millisecond. Okay, so the duration is all measured in milliseconds. Yeah, doesn't matter. Let's say 1 microsecond, which is more, more reasonable. And I have to use the same unit here. All right. Now, in linear search, how many comparisons do you need to confirm the only element in an array is or is not what I'm looking for? Just one. Yep. We'll still take one comparison. But this time, because it is running on a much faster computer, that comparison is going to take 1/60,000th of a second, which makes sense.
So he's faster.
Oh yeah. So Pat thinks, well, I'm winning by such a big margin that there's nothing to worry about. And then I said, well, yeah, well, you're winning right now, but let's see what happens when we double the size of the problem. So we double the size of the problem. Now we have an array of 2 items. With my binaries, let's change that. Let's bump it up to 3 because we want 2 to the power of something minus 1. It just makes things a lot easier to work with in that case. So in that case, how many comparisons do I need if I have 3 items in the array and I want to confirm whether a particular value is in the array or not? 2. I need 2 comparisons, and the duration is 2 because it's just proportional. How about Pat's algorithm? He would need, he or she would need 3, and so the number is going to be 3 divided by 60,000. Okay. If you look at these 2 columns, it takes me 2 microseconds, and it only takes the other computer 0.00005 microseconds. It's still way faster than my computer in terms of how long it takes to finish the algorithm. So next we double, quote unquote, double the algorithm again, double the size of the problem again. This time we go to 3 to the power of 3 minus 1. So my algorithm will take exactly 3 comparisons. And the duration, I'm not just going to do that anymore. I'll just say that it is the same as that number. And then Pat's implementation requires the same number of comparisons as there are elements in the array. And the amount of time is going to be that number of comparisons divided by 60,000 because that's the factor because of the faster processor, faster system approach. And you can see that in terms of the difference of the absolute value, it's actually increasing. In other words, I was only behind by a second because it only took me a second originally. And then now I'm off by 3 seconds. Next one up is 15. So instead of doing, writing 15 here, what I will do is I'll say the previous number times 2 plus 1. Previous number times 2 plus 1. So now I have 15, and now I can be fairly, lazy because I can just copy the previous row down here. Because with 15 items, which is 2 to the power of 4 minus 1, I will need 4 comparisons. And because it takes me 1 microsecond per comparison, it will take me 4 microseconds to come to a conclusion. Pat's algorithm will take 15 comparisons, but each comparison will only take 1/60,000th of a microsecond to finish. So that becomes the time. And Pat is laughing the whole time because the lead seems to be increasing as we double the size. So Pat is saying, hey, you can do whatever you want, double the size all you want, I'm just going to win by a larger margin. Maybe instead of, in addition to keeping my job, I can even get a raise. I can impress my boss and get a raise also. Okay, right? It sounds reasonable. So we keep this up for a while. Okay. And Pat is still laughing at when the problem size is 32,767, which is 2 to the power of 15 minus 1. Pat is still laughing. It's just saying, wow, look at this. I'm now winning by more than 14 seconds. But what Pat is not remembering is the ratio of these two numbers are closing. If you look at the ratio to begin with, this is a pretty large ratio. It is it's 60,000. Okay, so they're off by 60,000. If you look at the ratio of these two numbers, they're not quite 60,000 anymore. We're talking about 30 or so. Okay, so I'm catching up. Even though when you subtract this number from this number, that difference is actually widening still a little bit. So, Pat is saying, yeah, just keep increasing the size. I don't have a problem with that. So we'll keep going for, okay, let's see. That will be 1, 2, 4, 8. Okay, so at this point, Pat is starting to panic a little bit because, it seems like the gain is no longer that much anymore. Because if you look at these two numbers, he or she is still winning by about 14 seconds, about 15 seconds, and suddenly it's going back to less than 14 seconds. And now it is it's about 9 seconds, 10 seconds, okay? In other words, when you look at the absolute difference between the two algorithms, the gap is actually shortening. We are not even looking at the ratio, we are just looking at the absolute difference between the two algorithms. So I say, well, it's too late to stop the train now, let's double it again. Okay, and this is the last time Pat felt comfortable. Because when we double that again, look at this. My algorithm will take 21 microseconds, but the problem size is 2 million something. Pat's algorithm, or Pat's implementation, is now taking 35 seconds to search for a particular item in the array. And then Pat suddenly remembers, oh, but I forgot about that optimization that if the array is sorted, I can actually, on the average, cut the search time by half because I can use that trick, the trick that we talked about last time, right? Do you guys still remember that trick?
Too late now, though.
Oh, it's okay. I said, Pat, why don't you go back and change your program, put that in, and we'll continue the race, right? Pat puts that change in, and that changed the factor to what? It changed the factor to 1/2, right? Okay, so we'll do this part here and say this is another duration. Okay, modified linear search duration. And that's pretty easy to compute. It's really just this number divided by 2. Because on the average, you can cut the number of items to compare by 1/2 when you use the optimization. Okay, let's see how much that's going to buy Pat. Pat is saying, hey, I'm still winning. Let's double it one more time. Okay, and and it just keeps getting worse and worse because the boss says, well, this is only about 4 million items, but our actual database has more than 4 million items. Let's say that the actual database has 4 times that much. Okay, so the actual database has about 16 million items. And so, this is saying that my algorithm will only take 24 microseconds to finish the search, and Pat's algorithm, even with the optimization, will take 140 microseconds to finish the job. Okay. Do you think there's anything else Pat can do to improve this time, like upgrading to the what is the server grade processor?
Oh, the Xeon or whatever
the
they
Xeon,
are.
I think they're up to what, 12 cores?
Yes. Well, the other thing is your algorithm doesn't take into account the multiple cores, does it?
No, does not take into account that there are multiple cores. The multiple core helps a little bit because with a multi-core and you're doing a linear search, you can divide the problem into chunks. You can basically chop your array. If you have 12 cores, you can divide the array into 12 portions, and then each processor can do its own linear search within that portion. So yes, with a search algorithm, you can actually parallelize, especially in the case of linear search. But in the case of binary search, it doesn't really help you that much, because in order to get to the next chunk, you have to depend on the earlier one to decide whether to go there or not.
So the only thing you can do is copy your code.
Yeah, but even that is not going to help Pat, because what it is the shape of the curve is different. Okay, when you look at the curve, in terms of the problem size here, this is bar A bar, which is the size of the problem, and this is time, how much time it takes to finish the algorithm, to finish the problem. My algorithm is only the log of the size of the problem. In other words, it always looks like this. It increases fairly quickly at the beginning, but then it flattens out. Pat's algorithm, on the other hand, is linear to the number of items in the array. So Pat's algorithm is always a straight line. Okay, so it doesn't matter how you scale this thing here. You can scale it. You can basically scale this curve, the log curve, up, and you can scale this curve down. But eventually they will meet. There will be a crossover point where binary search will start to win. And this is the whole essence of time complexity. It also shows you that the constant. Now in this case, the constant determines the scaling of the vertical scaling. When I have a slower computer, my curve expands vertically like this. When Pat has a faster computer, it flattens it this way, but it doesn't change the shape of the curve. As a result, binary search still wins. Okay, and that's why as a developer, you really have to pay attention to the algorithm that you're selecting, not based on the complexity in terms of how many lines of code you require, but based on the time complexity in terms of how fast the algorithm executes. So right here, let's go to performance. This one doesn't have the big O notation, unfortunately. It doesn't use the same notation. But in terms of the big O notation, the linear search algorithm is big O n, or in our terminology, it is big O of bar A bar, which means the amount of time it takes to finish the problem or to solve the problem is linear to bar A bar. The constant is not important. It's just proportional to the number of items. But in my case, the other curve has a big O of the log of bar A bar. That means it is, oops, it's the wrong notation here. It means the amount of time it takes to solve the problem is linear or proportional to only the log of the number of items in the array. Okay.
How about theta?
Theta? Theta?
Yeah. So what is theta?
The theta means, I think it is one is the best time, and one is the average time, one is the worst time. There are basically three variants of the big O, and the big O, I think, is the worst case scenario. Yep. All right. Is that important stuff? The algorithms are not really that important because the most useful algorithms are already online. You look up Wikipedia, or you can go to a library. When you go to a four-year university, the library will have all kinds of research papers. So if you want to use a particular, if you have a problem to solve, chances are an algorithm already exists to solve that problem. So what you need to do is to look at the time complexity and say, but how long does it take to solve the problem? That is a very important factor. Are we doing okay so far with these concepts, even before we talk about the actual search algorithm itself?
Can you explain big O notation?
Yeah. Sure. Big O notation. So big O in algorithm. I think that may not be the big O notation that I'm looking for. Maybe it is.
Yeah, I see.
Has to do with the growth rate as x goes to infinity is left unstated, and one writes more simply that So basically, you're just saying that when one. Okay. Beginner's guide. Okay, big O of 1 describes an algorithm that always executes in the same amount of time because the constant is not important. Okay, so given a particular problem, if it only takes you always the same amount of time, regardless of the size of the problem, I can give you one example, bar A bar itself. Okay, how much time does it take to know the size or the number of elements in an array? That typically is a fixed time. So even if you have, whether you have an array of 1 or an array of 20,000 items, it takes the same amount of time to come back with the answer of how many elements there are in that array. So that is big O of 1 because the actual execution time is 1 times some constant k. But that constant k is not important. Big O of n is linear, and we have seen an algorithm like that already. In this case, if I replace n with bar A bar, that would be the complexity of the linear search algorithm. And then we have big O of n squared. We haven't really talked about any algorithm that is of this time complexity, but there are a lot of algorithms of this time complexity. A bubble sort algorithm has a big O of n squared, which means when you double the size of the problem, it takes 4 times the amount of time to finish the sorting. Okay. And then you have really nasty ones, like 2 to the power of n instead of n squared. Now 2 to the power of n looks really bad because it is exponential to the size of the problem. I can give you one quick example. Print all the combinations given you have x many digits, and these are binary numbers. It will take 2 to the power of n because there are 2 to the power of n combinations when you have n slots, and each one can be either a 0 or a 1. Is that making any sense? Okay. But I will tell you that that's not even the worst type of algorithms. There are ones that are worse than that. The ones that are worse than that is one that looks like this. It is proportional to n factorial. What is factorial? Factorial looks very harmless. Go ahead.
Multiplies by all the numbers down to 1.
Yep, n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 1. It seems pretty harmless. Okay, but n factorial actually grows faster than 2 to the power of n by a long shot. Okay. So there are algorithms that are basically saying well it's going to take a long time to finish or to solve the problem. And I'll give you one example like that. I think I'm going to take a little break from our usual algorithm discussion and just talk about stuff that are related to algorithms, but I'm not going to give you the exact details of how the algorithms work out. I usually have at least one person working for FedEx or UPS or the USPS. Does anyone work as has anyone worked as a truck driver for any one of those companies? Has anyone delivered pizzas? Okay, driving? Okay. So typically how many pizzas do you carry when you have, during the busy times?
2 or 3.
2 or 3, okay. So when you have 2 or 3 destinations, how do you decide, what is the best route to get through all 3 destinations?
We just go like time-based. Whoever ordered first gets first.
Oh, okay, so it's first come, first serve.
Yeah.
Okay. But let's say, your company decides, okay, in order to save fuel and also save time, overall the driver time, they want to optimize it. Okay, so if you have 3 drops to make, somebody will figure out, okay, in which order, of the drop-off will save you the most amount of time. Will take the shortest amount of time. Okay, does that make sense? That this will be a problem that some people will want to solve. Okay, with 3, it's not too hard. Okay, because how many combinations do we have? Let's say you have destinations A, B, and C, and we want to enumerate all the possible orders of dropping off pizzas in that case. Okay, you have destinations A, B, and C. Okay, these are the 3 clients that have ordered the pizzas. So you have A, B, C, you have A, CB, and then you have BAC, BCA, and then you have CAB, and then you have CBA. There are 6 ways to do it. Okay, we call these 6 permutations. Okay, and 6 turns out to be, guess what? 3 factorial. Now it works out this way because when you have 3 slots to fill up. When you fill up the first slot, you can choose any one of the 3 choices. You can select A, B, or C. So there are 3 choices for the first slot. But when you have already decided on the first slot, you only have 2 choices left for the second slot. So the second slot only has 2 choices left. But once you have decided the first and the second slots, the third one only has 1 choice because you only have 1 destination left. So when you multiply 3, 2, and 1, you get 6, and that's exactly 3 factorial. And that's why factorial is useful here. Okay. You can write a very simple algorithm to enumerate all possible combinations, figure out how much time each one takes, and then pick the best out of the whole bunch. Does that make sense? So we can figure out, if I go to the destinations in this order, this will take, let's say, 60 minutes. I guess that's too long for pizza delivery, huh? Let's say this is 6 minutes, okay? This one will take 5, and this one will take 7, 5.5. This one will take 6.5. So, once you figure out, how much time each route will take, then you can easily determine and say, oh, okay, we'll go with this particular route because it will take the least amount of time. Okay, does that make sense so far? Okay, so, and this algorithm is not really too difficult to write, not at this point, but later on in the class, once we understand what is recursion and subroutines, this one is actually pretty easy to deal with. Okay, so let's just say that you wrote an algorithm to solve this problem, working for a pizza place, which typically only has, maybe 3 to 5, drop-offs with any particular route. And your boss is so impressed with your program that your boss decided to talk to some other people and say, maybe some other people will want to buy this program too because it is so useful. So your boss decided to talk to someone who works for, let's say, UPS or some sort of courier company where they have to drop off packages. What is the number of drops per truck when you work for UPS? 3, 5. It's probably close to 100. I don't know the exact number. Would 50 be a good one? Do you think 50 packages would be a good underestimate of how many stops they have to make? Let's say 50. Okay. So your boss sold your program to UPS for X amount of money, and then the next day you went back to the pizza shop to continue with your programming job or your pizza delivery job. Your boss told you you're fired. But boss, why? Well, because your program sucked. It didn't work. What do you mean it didn't work? I mean, I worked out this part here. It came back with an answer like right away. Then your boss said, but when I tried to demonstrate this program to UPS, it just hung up. It didn't crash, but it didn't give me an answer either. Why is that?
The problem's too large for it.
The problem is too large. And then your boss says, we have 3 stops, UPS has 50 stops. What is the big deal? 50 stops only. Well, but then you're not looking at 50, are you? The amount of time that the algorithm requires to solve the problem is not 50. It is 50 factorial. Now, how big is 50 factorial? It doesn't sound that harmful. I mean, surely it cannot be as bad as 2 to the power 50. Let's figure it out. I don't think I have a calculator with this, so I'll use, hey, guess what? I can use the spreadsheet because the spreadsheet has factorial. Okay, so we'll use, factorial, okay, factorial of 50.
3 times e to the 64?
Yep. This is 50 factorial. How many people know how to read the scientific notation?
Not me.
Not you? Okay, I will describe what it is. It is 3.04 and something times 10 to the power of 64. In other words, imagine after the 3 you have 64 zeros. Okay, that's the ratio. Okay, the pizza place will have 6. Okay, 6 units of time to finish the problem. It can be 6 microseconds. It can even be 6 nanoseconds. I don't care. I mean, you can have 6 nanoseconds in this case, and in the other case, you end up with 3 times 10 to the power of 64 nanoseconds. A nanosecond is a very small fraction of a second. But when your power is 10 to the power of 64, that will still take a lot of time. Let's figure out how much time it actually represents when the unit is 1 nanosecond. Okay?
Nanoseconds a millionth, right?
Huh?
Millionth of a second?
A nano is
To the -9?
it's a billionth.
Billion.
Yeah. So when you want to convert this to seconds, it will be this number divided by 1 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So you end up with this many seconds. Wow, that's a lot of help. How many seconds are there in a minute?
16.
60 minutes, 60 seconds in a minute. So this is the number of minutes that you need. How many minutes in an hour? 60 again. This is the number of hours. How many hours per day?
Maybe waiting for a while for that program.
How many days per year?
366.
Oh man.
Okay,
Like
so 365.24 something. I mean, therefore the leap year thing. Okay, it would take 9.6 not years, but 9.6 times 10 to the power of 47 years. There's not enough time in the universe to,
Wow.
to do this.
Oh, it's a terrible algorithm.
Huh?
So that's a terrible algorithm.
Hang up for a long time.
Okay, now that you just brought up a very good point. That's a terrible algorithm. So maybe your boss has ground to fire you because you wrote a very terrible you have a terrible implementation of the algorithm. Sorry?
Great algorithm, something small.
Yeah, that's true.
Yes.
Yeah, exactly.
So how are you going to keep your job? Your boss says your algorithm sucks. So how do you keep your job? Yep.
Tell him that's okay. I'll go work for UPS then.
Well, you can argue it this way. You can say, but boss, listen, this is called the traveling salesman problem. Okay, and it is. Okay, it's called the traveling salesman problem, which has the same problem. You have so many cities to travel to, and then you have to figure out what is the best way to traverse each and every city, only once and only once. So it's a classic problem. People have been trying to solve that problem, with an efficient solution, for decades already. And your problem is, basically the traveling salesman problem. And then you can tell your boss, over the past, let's see, this is 2012, and let's say computer science starts in 1950. So over the past, 62 years, you have all kinds of geniuses trying to work this out, and nobody has come up with a solution that is faster than n factorial. There's just no way. Okay? So you can tell your boss, I may not be a very good programmer and come up with this particular algorithm, but over the past 62 years, this is the best the brightest minds can come up with too. So good luck with your next hire. Yep, go ahead.
It's easier just by visual means because my family works similar to it. We get work orders, go to houses and clean them and whatnot. And we look on a map with all the destinations. We just visually place them in order which ones.
What you're doing is you're making use of heuristics. And when you make use of heuristics, you're optimizing it based on certain rules of thumbs. So in your case, it's a visual because you can see all the dots clustering. Then within the cluster, you can still do optimization if you want to, but it may not be even worth the time to optimize at that level because you may be gaining by 30 seconds or a few minutes, which is not important. But if you want the absolute best solution, this is the way to do it. Okay? But the bottom line of the discussion is This type of problem belongs to a very special class of algorithms. It's called the NP-complete class. NP-complete. What does NP-complete stand for? N stands for non-deterministic, and P stands for polynomial time. Non-deterministic. What does non-deterministic mean? Non-deterministic means, let's pretend you have a supercomputer with an infinite number of cores and almost infinite memory bandwidth. Okay. In other words, each core can talk to memory in its own memory bus. So if they're not using, there won't be any memory bus congestions. So that's what N stands for. Non-deterministic means infinite core processor. It will still take that processor a polynomial time relative to the problem size to solve the problem. So that's a very special class of problem, which has that particular property. So are we doing okay so far?
Is there a real world solution for this, or is that it?
Is there a what?
Is there a real world solution to this, or is
No.
that it?
No, there's no real world solution to this. And yet it is a very practical problem that people have to solve. Not only for UPS or pizza delivery places, but also when you have a compiler, the compiler has to do optimization of how it uses the registers efficiently, and that turns out to be the same type of problem too. So a lot of optimization problems boil down to the traveling salesman problem. And all of those problems cannot be solved efficiently. There's just no known solution to solve those problems efficiently. They're called intractable. Basically you can solve them, but the amount of time it takes to solve these problems often make the solution pointless because it would take so much time to come up with a solution. Okay. Now these are topics that you will encounter when you go to a 4-year university and take their classes called algorithm analysis and also automata theory, which are fairly high level, almost purely math classes. But in terms of the context and also why these topics are important, I have just illustrated that. So are we kind of okay with the concepts? Not the details, but just the concepts. So this is a little digression from our binary search algorithm because I do want to show you, in a broader context, what do we do with, how do we know how much time it will take for an algorithm to solve a problem, and are there problems that are solvable, but it will take so long to solve the problem that there's no practical solution to do it. Now what people do with this type of problem, the NP-complete problems, is they oftentimes will basically say, okay, let's just say I don't need the most optimal solution. Now, when you say that you don't need the most optimal solution, just something that works well, then you have the other algorithms. You can visually eyeball the destinations and just say, okay, these belong together, and these belong together, these belong together, and then you can simplify the problem a little bit. It will not give you the absolute most optimal solution, but from the practical standpoint, the solution is good enough, and that's all that counts. All right, so now let's go back to our regular discussion of the binary search algorithm, and then we'll go figure out how we can write an algorithm like that. So I'll call this tag versus Pat. Yep, I think that would be a pretty bad day for Pat. Getting all the hope up and then just get shot down later. All right, so getting back to where we were before, I'll bring this up again. Okay, this is our binary search by hand. These are values in an array, and the gray portion of each column says how many of the items can we rule out. Binary search starts with the middle element, and then you have only 3 choices. When you compare the value that you're looking for with the value of the middle element, only 3 possible outcomes are possible. 1, you have just found it. Unlikely, but sometimes it happens. You can also have the case where the value that you're looking for is smaller than the value at that particular location. In that case, because the array is sorted in a non-decreasing order in this case, you can also rule out everything after that. On the other hand, in the second test case, in this case, we have the element that we are looking, the value that we are looking for being larger than the value of the element. In that case, you can rule out all the values before the element. So by combining these operations, if you have ruled out everything, then you know the element, the value does not exist in the array. Are we doing okay so far with the manual method of doing binary search? Okay. So if you want to, and if you want to visualize it, it's basically having a stack of cards. Each one has a number on it, and the entire stack of cards is sorted. So what you do is you pick the middle card out of the entire stack, separating the stack into two stacks. By comparing the one card that you pick out and the value that you're looking for, you have three possible outcomes. You can say, yes, I have just found the card that I want, or you can toss away that card along with either half, one or the other half of the stack. And then with the remaining half of the stack, you do exactly the same thing until one of two things happen, until you either have found the value that you're looking for, or you have no cards left. You have to just chucked the entire stack of cards. Okay. So now we want to write an algorithm to do exactly this. How do we go about doing that? Okay. First of all, is this approach repetitive? Am I doing something again and again? Yeah. What I'm doing again and again is picking the middle element out, comparing that, and then potentially, remove one half of the stack. That's what I'm doing repeatedly. Okay. So I'll call this binary search algorithm. And in revision 1, all that we want to do is to say that, yep, it has some kind of loop here. And when do I exit?
Find it or you're out of it.
Okay, very good. So we'll just say that, in very vague terms, we'll say we can exit when we find the element that has a value of k. Okay. Or what is the other way we can get out?
When you run out of possibilities.
When we run out of possibilities, okay, we'll just write it that way. When we run out of possibilities. In other words, we confirm that no element has a value of k. Okay. And I'll even call this one revision. As vague as it is, and it doesn't really tell me what to do or how to do it, I'll call this one revision. Because it is important. It already captures some of the really important parts of the algorithm. It's just that we don't have the ability to express that just yet. Okay. All right. So in the next revision, instead of saying this element, that element, and so on and so forth, maybe we should introduce the terms of an array and also use a variable to indicate which element are we dealing with in this iteration. So we'll go ahead and say, we have array A contains the elements, and then we'll use, variable M is the index of the element that we are examining in an iteration. Okay. And we'll just also make it very clear, the variable k stores the value that we are searching for. Okay. So given these definitions, which I think make sense, how can we make our algorithm a little bit more specific? Instead of using those vague terms, can we at least deal with this one? Now that we know what A, M, and K are, how do we confirm that we have just found it? A bracket M equals K. Okay, that's pretty good. At this point, I don't even know, how I can get to the value M. But since I just say that, well, let's let us assume that M is a variable that controls which element we are looking at. Okay, we can just make use of it. We don't really quite have the vocabulary to talk about how to express the fact that we are running out of possibilities. So we'll leave that one the way it is. And then this is another revision of our algorithm. It's still kind of vague, but it's a little bit more specific now. So now in revision 3, what we want to do is to say, but how do we remember which parts of the array cannot have the value that we are looking for? Well, you can look at it in 2 ways. Okay, let's switch back to the spreadsheet. You can either look at it from the perspective of which area is grayed out, or you can keep track of the area that is not grayed out. Okay? Keeping track of the area that is grayed out is a little bit more work. Okay? It's actually it's less intuitive. It makes sense to keep track of the area that has not been grayed out yet. So let's go ahead and just use this as an example to illustrate the area that can still contain the value that we are looking for. Okay. Before we perform the first comparison of what we cannot rule out anything. That means the entire array may contain the value that we are looking for. Is that making any sense? Before the first comparison, we cannot rule out anything, and as a result, the value that we are looking for can be possibly anywhere within the array. So if I want to use a particular color to indicate the area, I would basically highlight the entire thing. So let's pick a brighter color. In this case, I'll just pick a bright yellow color, like that. Okay. So before the first comparison, this is what it looks like. The entire thing can have the value k. After the first comparison, we only have this much area remaining that can possibly have the value that we are looking for. After the second comparison, previously after the first comparison, this is after the second comparison. After the third comparison, we have only 1 square left. After the fourth comparison, nothing here is yellow anymore, because no element in the array can possibly have the value that we're looking for at this point. Now this one doesn't show it as well as the second one. Okay, let's do it with this one too. Before the first comparison, the entire array can possibly contain the value that we are looking for. After the first comparison, only this much area can possibly have the value that we're looking for, because we have confirmed the other part does not. After the second comparison, we have these 3 squares left. Now this is important. Do you see how the other ones down here are no longer considered? Because they are all ruled out by the first comparison already. After the third comparison, I only have 1 element left that can possibly have the value that we are looking for. And then after the fourth comparison, there's nothing left. In other words, what I'm trying to propose is, instead of keeping track of the gray areas, I want to keep track of the yellow areas. What is the best way to keep track of the yellow areas? It seems like it has a start index and an end index. So we can just use 2 variables. One variable to keep track of the index of the beginning, the first element that can possibly have the value that we're looking for, and then use another variable to keep track of the index of the last element that can have the value that we're looking for. Is that making any sense? I'm just having 2 bookmarks. One bookmark to mark the beginning of the range, and another bookmark to mark the end of the range. Okay, so that's what we'll do. Is in the algorithm, we'll add 2 more variables. We'll have variable b is the index of the first element that may still have value k, and then we have variable e for end is the index of the last element that may still have the value k. Okay, well this is cool. Now, given that, do we know how to initialize b and e? In other words, before the first iteration, how should I initialize b and how should I initialize e? Before the first comparison, what is the index of the first element that can potentially have the value that I'm looking for?
0.
0. It's not 1, it is 0, because 0 is the index of the first element. What is the index of the last element?
A bar.
A bar
Yeah.
minus 1. Very good. All right, so right off the bat, we know how to initialize B and E. And then we just copy and paste this loop here. Okay, and we'll just call this another revision, okay, because we did some work already. But you can see, when I write or when I design an algorithm, I don't do it from end to end, like start with line 1 and then just keep going, because I need to look at the structure of the code and just add a little more details each and every single time. All right, so we look at this algorithm, and it's time to do some work with okay. But for each iteration, what do we do? Well, let's take a look at the manual example, and we'll start with this one. What do we do per iteration? Each column is one iteration.
Find the center.
We have to find the center first,
Yeah.
okay? So how do we find the center element or the middle element? The index of the middle element.
Your max, the end of the index divided by 2.
Yep, the beginning plus the end divided by 2. Basically, it's the average of the beginning and the end. Is that making any sense? Well, let's check whether it makes sense or not. In the first iteration, this is the range, and this is the middle. In the second iteration, this is the range, and this is the middle. In the third iteration, this is the range, and that's the middle. And in the last one, it is both the beginning, the end, and also the element that we want to compare. So that seems to make sense. We'll end up with a problem later on, but for now, we'll just say that M, which is the index of the element that we are looking at, is nothing more than the average of B and E. So we'll just say B plus E divided by 2. This will work for the most part because of the way I choose the number of elements in the array, but I will show you later on if that doesn't work out exactly, how do we deal with it. But for now, we'll just say it's just the average. Okay, then if we switch back to this, what do we do per iteration? Once we identify which element we want to compare to, we perform the comparison. So what do we do with the results of the comparison? How many outcomes are possible out of that comparison? Well, there are 3 actual outcomes. One is not very useful, but there are 3 possibilities. So that means in my algorithm, I will probably begin with just saying, okay, there are 3 ways they can compare. In other words, I can confirm A bracket M is less than K in one case. I can confirm A bracket M is greater than K in the other case. And I have one more case, which basically means they are the same. Is that making any sense? All right, let's find out what do we do when A bracket M is less than K, assuming the array is sorted in a non-decreasing order. Well, nothing is better than just going through one of our examples and find out what we have to do. So the case here is the element is less than the value that we're looking for. Okay, the element is less than the value that we're looking for, so we are looking at column C in this case. So in column C, what are we doing? Are we moving the beginning of the range, or are we moving the end of the range? We're moving the beginning. Because you can see before the second comparison, we can have these elements can potentially have the value that we are looking for. But after the comparison, we only have these left. So the end has not changed, but the beginning went from row 1 all the way to row 5.
I was thinking you were doing it for the first one.
Oh, no, for the second one, because it's handling the case where A bracket M is less than K. Okay? So that means we have to change B because we are moving the beginning of the range. But how do we move B? Let's take a look again. This time look very closely. The range used to be here to here. In other words, this was B and this was E. The range became like this after the second comparison. So the beginning went from here to here. This is M. is m plus 1. Very good. Now, in this case, the plus 1 is very, very important because without the plus 1, it will still kind of work, but it won't stop. The algorithm in the end may get stuck in an infinite loop. Now, does it make sense that it's m plus 1 instead of m? It makes perfect sense because the comparison has just confirmed that a bracket m itself that is not what we are looking for. So you have to rule that out, which means the beginning index of the elements that can have the value k cannot be m itself. You have to start with the one after m. So it does make sense to have that your plus 1. But once we know how to handle this one is kind of symmetric but reversed. So we can still look into our algorithm. That would be column B. Before column B, before the first comparison, we can say that the entire array can potentially have the element or the value that we are looking for. After the first comparison, in which case a bracket m is greater than k, a bracket m is greater than k, we have to move which end of the range, the beginning or the end. We move the end used to be 15, and now it is 7. M is 8. So how do we express that in an algorithm? We're changing e to become m minus 1. So once again, the minus 1, it doesn't look very important, but it is very important because we already know the element at index m is not what we're looking for. So the index of the last element that can have the value that we're looking for has to be the one before m. A bracket m itself cannot possibly have the value that we're looking for because we just confirmed that in the comparison. What about this case here? What is that? If I get to this part of the algorithm, what does that mean? That means they're the same, right?
Yeah.
But when they're the same, I really don't have anything to do because the loop already is checking for it. In other words, I know that the algorithm will get out, will exit when a bracket m equals to k. So there's really nothing to do in the conditional statement. There's nothing special to handle in that case. Yep.
Don't you need to specify if it's not in the array? If the number you're looking for isn't in it, isn't that what you put in the else?
In the else here, this else represents what if the element, what if I just found an element in the array with that value? Because to get to this part here, a bracket m is less than k has to be false. A bracket m is greater than k has to be false, and so the two have to be the same. Because I'm not answering your question.
Yeah, but what if it's in between the two? Like if you're looking for an element that's not in the array,
right?
Like we were in the examples,
right?
It would just keep repeating.
It will not keep repeating. Okay, that's a very good question. Let me rephrase the question and call this one revision at this point. The algorithm is not done yet because we still haven't handled the case. What if the element does not? What if the value is not in the array? That's what you're asking. In other words, we still don't have a way to answer this particular question, right? Okay. So let's think about it, from a kind of quote-unquote graphical perspective. This is the beginning of the array. This is the end of the array. So B is initially 0. E is initially bar A bar minus 1 because we cannot rule out anything before the first comparison. After the first comparison, either you move this one to here, or you move this one to here, or you conclude that the middle element turns out to be the value that you're looking for, right? After the second comparison, either you move this one or you move this one. So every time for each iteration, the B and E will get closer and closer together. The question is, at the very last iteration, when B, E, and E are exactly the same, which means M would be the same as B and E because the average of the same number is the number itself. In that case, what if that element is not what you're looking for? That's what we are asking. Okay. So let me write it down first. Okay. So comments. How do we exit? How do we exit when the value k is not in the array. Okay, that's what we're asking for. Now when you look at this code, you already know that B has to increase or E has to decrease for each iteration. As long as we have not found the element, one of these things has to happen, right? So what that means is B and E eventually will become the same. Okay, so let me just write it down here. From an analysis of the algorithm, we know that as long as A bracket M does not equal to K, B has to increase or E has to decrease, right? At some point, B will become the same as E, which means M would be the same as those two too, because the average of two numbers that are the same is the number itself. So in that case, what's going to happen? Well, let's find out. M, B, and E are the same after this statement. And yet, we know the value is not in the array. So either this has to happen, or that has to happen. If this were to happen, what becomes the value of B? B becomes 1 more than M, which also means it's 1 more than E, because M and E are the same. Okay. What if it is the other way around? Then E has to decrease by 1, which means E will become 1 less than B and M also. Okay. So what we have here, just from just a casual analysis of the code, is it doesn't even have to. We don't even have to know that they will close in by 1/2 of the distance every single time. We know that they have to get closer. As they get closer and closer and closer and closer, at one point they will overlap. When they overlap, is not an issue because it means that we have one single element left that can have the value that we are looking for. But after that comparison, they will cross over. Now, when they cross over, what does it mean? Okay, so that means undo. Okay. After this iteration, B and E will cross over, which means B is going to end up greater than E. Now, what does it mean when B is greater than E? What is the definition of B? B is the index of the first element that can contain the value K, and E is the index of the element, the last element that can still have the value K. When they cross over, what does it actually mean?
Means it's not in the loop.
There's nothing left. There's nothing left because you're specifying a range of no elements. Because no element can have an index that is at least B and at most E when B and E cross over. So that's the exit condition. Okay.
So would you say if B is equal to exit?
Sorry?
So then would it be if B is equal to E, then exit, or what?
No, when B is greater than E. Because B is always, okay, it only makes sense as if you have anything left in the array, if you have any elements left in the array that can still have the value K, B and E cannot cross over. In other words, B and E can at the most be the same, which means the beginning of the range is the end of the range, and you have one element left to compare. But when B is larger than E, then you cannot find any element with the index at least being B and at most being E.
So if that's true, then there is no, then value K is not.
That means you have exhausted the entire array. Nothing in the array can possibly have the value K, and then you can exit in that case. Okay. So that means if I want to go for the second last revision, we now know how to express the fact that we run out of possibilities because we just talked about that. Basically, when B is greater than E, we're done. Yep.
Say, for example, bar A bar was number of students in class for last name, but the same last name. When it
Well, binary search will only look for the existence of at least one element of the value that you're looking for. If there's a duplicate, finding one or the other is counts as an answer. Because we just want a confirmation, does this value exist in the array? If you have two people or two elements fitting that particular value, having the same value, finding either one is a confirmation that yes, at least one value in the array matches what you're looking for. Yep. Ah, very good. So the question is, what if we have an even number? What if B and E are both even numbers? No, they're both. One is an odd number. They add up to an odd number. Okay. Okay. So what do? Because in that case, we have two middle elements. Just think about an array of 4 elements. Okay, we have 1, 2, 3, 4. We know the first and the last cannot be the middle ones, but then we have 2 middle ones. College hour, no.
Go to the
Huh?
Go to the hackers.
Oh. But in this case, we know the second and the third elements can be both considered the middle element. In that case, you can randomly pick one if you want to. It doesn't matter which one you pick. It doesn't even matter whether you pick it consistently. You can sometimes pick the one that's closer to the beginning, other times pick the one that's closer to the end. It will still work out. But just for consistency, the way we do it is to use the floor function to do it.
I was wondering about that.
Okay, the floor function is already described in the notes, but I'll just describe it here, once. So I'll say, the floor of x is the largest integer that is less than or equal to x. That's the definition of the floor function. Let me give you a few examples and make sure that you understand what is the floor of something. What is the floor of 2.5? What is the largest integer that is less than or equal to 2.5? 2, very good. What is the floor of 16? 16 itself, because 16 is already an integer and it is less than or equal to itself. What is the floor of negative 1.5? Negative 2, very good. It's not negative 1, it's negative 2 because we are looking for the largest integer that is less than or equal to 1.5. So it's negative 2, very good.
So like the birthday function, it's a stepped function. So you once you get past a certain age, you don't say you're 17 and a half. So you have that stepped function.
So you're talking about if it's more than a half, you round up, and if it's less than a half, you round down.
You can't round up. You can only round down.
That's it's also called truncation. In this case, 4 is the same as truncation as far as non-negative numbers are concerned. But once you go negative, truncation means negative 1.25 is negative 1 because you're just tossing away the fractional part. But when you're using the floor function, it becomes negative 2 because you're always taking a step down. You're not just losing the fractional part. Yep.
So both times if you find the value, it exits, and if you don't find the value, it also exits.
Yes.
How can you tell which is?
Very good. Let's figure that one out. But before we figure that one out, we have to make this a specific kind of loop, either pre-checking or post-checking, because the way it is right now, we're just saying that it is a loop. We know how to exit, but we haven't really decided whether it's a pre-checking or a post-checking. What do you think? Should it be a pre-checking loop or a post-checking loop? In other words, do I have to go through at least one iteration? Yes. We do. Okay? And we can't really make it into a pre-checking loop conveniently because the condition relies on the value of m. But where do we get the value of m? The value of m is set in the loop body itself. So that means in order to even perform this comparison, we have to go through at least one iteration. So that means it is natural to express this as a post-checking loop and not a pre-checking loop. So that's an easy one. Repeat and until. And then we'll answer the other question. The other question is, yes, the loop is going to exit, but we do not know the answer yet when it exits. So we want something that looks like this. If blah, 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 then conclude k is in the array, else conclude k is not in the array. Right now, we don't have the mechanism to specify quote unquote a return value to indicate the result. So we'll just use this kind of statement to say that okay, we can conclude it one way or another way. So the question is, what do we put inside the parentheses? What is the condition that will let me conclude that k is in the array? Well, we have to kind of go back and figure out what are the two reasons we can get out of the loop to begin with. That will give us a clue. Well, they all spelled out here. The two reasons we can get out of the loop is a bracket m equals k, and then the other reason we can get out of the loop is b is greater than e. Which one do you think helps me conclude that k is in the array?
First one.
First one, okay, it's just staring you in the face, right? A bracket m equals k, and that's it. That's the entire algorithm. Because if a bracket m does not equal to k, and yet I'm out of the loop, what has to be true?
It's not in there.
B is greater than e has to be true. But I have just talked about or argued that when b is greater than e, that means none of the elements in the array can have the value k. So in that case, I can conclude k is not in the array. That's it. That's our binary search algorithm in its entirety. So what I'll do is I'll give you a homework assignment based on the binary search algorithm. The algorithm is already done here. So what I'll do is I'll give you test cases. Okay, 3 test cases. Just like with the find the maximum of 2 variable homework assignment, you will have to trace it. If you want to use pre and post conditions to prove the algorithm is correct and it will complete its job, feel free. I'm not going to do it. I'm not even going to grade it.
So don't worry about it.
I was going to say that's a long.
Yeah,
a lot
it's
of grading.
really long.
Yeah.
Really long.
Yep. I think we still have 50 students in the class, so grading the exam was just it just takes a lot longer
How is
than
that
I
going?
thought.
That's why you got to be stricter with your with who you let in.
I used to have multiple choice questions, and I let people do it, in the lab, using Moodle. So that was a non-issue. I can give you guys like 100 questions. It doesn't cost me anything to grade. But now it's all open-ended questions. I have to do the scanning. Well, first of it's just the destapling and restapling takes quite a bit of time.
Why don't you get your kids to help you?
Because they got their own homework to do.
Oh.
I thought about that too already.
Yeah.
Call it training to be a instructor or an educator.
Yeah.
Exactly. Most of your time
Teacher's aide.
doing homework still.